So today we're going to be solving another AMC 10A problem. This is from the 2017 AMC 10A and it's problem 20. And this problem uses a bit of divisibility rules and some modular arithmetic. And it probably doesn't look like that, but these techniques will later come in handy in solving this problem in a really creative way. So let's read the problem first. So let S of n equal the sum of the digits of positive integer n. For example, S of 1507 would equal to 13. Well, it's pretty straightforward why. And for a particular positive integer n, S of n is equal to 1274. So which of the following could be the value of S of n plus 1? So instinctively, we would all think, oh, one possible value of S of n plus 1 would be 1275, because if you add if you add a value of 1 to n, if you add a value of 1 to n, then if no digits of n carry like values, then this would just increase by 1. So 1275 will be a possible value of S of n plus 1. But as you can see, 1275 does not exist among these answer choices. So we'll have to solve this problem in another way. So, and we can't just try to bash this problem and try to find an n that works for this. And yeah, the sum is a pretty large number, so that is not a good idea. So what we want to do here is find the relationship between S of n and S of n and n. So one way is, so some of you will be familiar with this, the divisibility rule for 9. So the divisibility rule for 9, if we kind of write it in the form of modular arithmetic, we can say that n has the same remainder as the sum of its digits when divided by 9. And as you can see, so if you don't understand, so those who know some modular arithmetic will understand why the fact that n has the same remainder as S of n when divided by 9 can be written in this form. And if you don't really know what this sign means and what this statement in general means, then feel free to go to my number theory playlist to watch the I don't know how many videos there are on this, but the videos on modular arithmetic, and then come back to know what this means. It is a pretty crucial skill in number theory problems. So we got this relationship, but here we know what S of n is. It's 1274. So S of n is equal to that. So that means that S of n will be congruent to 1274 mod 9. Well, it's pretty obvious, I guess. They're the same anyway. And I'll just write that around here. But then we know that 1274 has a remainder of 5 when divided by 9. Because 1269, wait, never mind. It has a remainder of 5 when divided by 9. So 1274 is congruent to 5 mod 9. So we know that n is congruent to S of n, which is congruent to 5. So we get that n is congruent to 9. No, n is congruent to 5, sorry. N is congruent to 5 mod 9. There we go. And yeah, we found the relationship between n and S of n. And then we use the value of S of n in this relationship to find a statement for n. And now we have to deal with n plus 1 now to find S of n find a kind of something describing S of n plus 1. So n plus 1 will be congruent to, so you know how in modular arithmetic you can add values on both sides of the equation. So if I add 1 on this side, I have to add 1 on this side. So 5 plus 1 will be equal to 6. So n plus 1 is congruent to 6 mod 9. And from this statement, we can conclude that n plus 1 is congruent to S of n plus 1 mod 9. So S of n plus 1 is congruent to n plus 1, which is congruent to 6. So S of n plus 1 will be congruent to 6 mod 9. Ooh, we finally got a statement describing S of n plus 1. So now we didn't really get a value for S of n plus 1. Well, there's like different possible values for so many different possible values for S of n plus 1 if S of n is equal to 1, 2, 7, 4. But now we got a statement that has to be true for S of n plus 1 and for any S of n plus 1 in this case. So we can just test it on each of these values, A, B, C, D, E, to see which one actually satisfies this statement. So for A and B, it's so obvious, no, because they certainly do not have a remainder of 6 when divided by 9. So not A or B. And certainly not C either. 12 has a remainder of 3 when divided by 9. So, no. At 1, 2, 3, 9, it has a remainder of 6 when divided by 9. So this seems like the answer, but we'll check E as well. But 1, 2, 6, 5 has a remainder of 5, I think. Yeah, a remainder of 5 when divided by 9. So no, E doesn't work either. So that means that only D works in this. Only D satisfies this. So D is the answer. So overall, this problem it's a pretty simple solution, but overall, it's a really creative solution because if you just read the problem, you can't really it doesn't really seem like a divisibility rule problem or like a problem that uses like remainders and modular arithmetic, but we use that method to really easily get an answer for this problem. So what I really liked about this problem is that, yeah, we kind of use like an unexpected method thing. So we kind of like thought outside the box. Like, it's pretty creative. And yeah, but basically what we were trying to do was like we're just trying to find the relationship between n and S of n, and then use that value of S of n to find a statement describing n. And then use this relationship to find a relationship between n plus 1 and S of n plus 1. And then use that relationship to find a statement describing S of n plus 1. And then check each of the answer choices to see which one actually satisfies that statement. So that's basically what we did. And yeah, so hope you enjoyed this video and see you in the next videos.